And then I think we can start. Welcome, everyone. Thanks, Dr. Shaheen, for continuing to give us this really valuable series on AI in healthcare. I think this is the fourth one in the series. So I'm looking forward to learn more from you. The floor is yours.
Yes, I think this is number six, actually, believe it or not. So, all right. Hello, everyone, and thank you for taking the time on a Friday evening to talk about machine learning. And this talk is more about some of the technicalities of what machine learning entails. And one would ask, why would I, as a physician, care about how the machine works? It is simply because, first of all, it's a lot of fun. It's not as hard as people think, or at least I try to make it as easy and straightforward. And it's also important for you to understand because it gives you an idea of where it actually can be faulted and what kind of errors or biases it actually can produce by knowing how it actually made its decision. And at least when you can do that, because some models are black boxes, and that's a bigger problem that we can actually cover in this. So that's why I wanted to give this talk to non-technicians and AI to better understand what machine learning entails. So we are talking about principles of machine learning. Remember this slide from a past lecture where we said we typically see in three dimensions, and we consider our time to be the fourth dimension. And some physicists said there are fifth, sixth, and seventh dimensions, and these are necessarily like if you have a plane world and you just warp it or something like you do with quantum physics. And this is the model that you actually can think of how you can create additional dimensions. But eventually, it's if you think of X, Y, and Z, the machine is able to see in way more dimensions than three. X, Y, Z, A, B, C, Z. So if you actually go with the rows of your Excel sheet, every column becomes sort of a dimension for that model that actually sees the world through. And based on these dimensions and the distances between the point of contention or decision making and all other dimensions and its world and their averages, that is how it makes its prediction or its classification or its regression or whatever it actually ends up doing. And that's what actually gets translated into a decision. So the first kind of form of learning in machine learning is the traditional one, what's they call supervised learning. So this is basically every time you have a data set that you train on that has like a label. So you have 1 million patients with cancer diagnosis, and you have all the parameters. And at the end of that, you have a parameter that's called cancer yes and no. So you have labeled the ones that have cancers and the one that not have cancer, and you actually use that data set. And typically what people do is they split that data set, sometimes 50-50, sometimes 20-80. It depends on how big it is and how robust and into like global they want to make it. And they train on a set and they test on a set. And they have a training score and then a testing score, and they say, okay, this model is 89% like accurate in its prediction. So this actually relies on you doing the labeling. It's very important for us to know that this actually needs our kind of labels. Without that, the model is useless because it cannot go and learn anything. So it learns from our knowledge. There is a very important concept as we talk about learning and about how it reaches a decision, which is regression versus classification. Now, these are not stuff that we actually are trained on in like our whatever math we took before going to medical school. But basically, classification is more for nominal uh, uh, values where you actually classify cancer, no cancer, or type 1, type 2, type 3 of something. This is what actually becomes a classification. There are classes that are like distinct entities. Whereas regression is more for continuous numerical values, where you say, well, this value that is sitting in the middle, based on this, it will regress to this or that, and how this is how I'm going to actually take it, or I am going to actually calculate where it actually resides on all these decision data points, and then make a decision about where it actually falls. So these are two distinct ways of the equation for labeling whatever is unlabeled that you are trying to do. So classification, again, it's like for qualitative labels: cancer, no cancer, dead or alive, so and so. Whereas regression is more quantitative: how many days they're going to survive, hospital length of stay. So it thrives on numerical values, not just yes and no or categories. And the metric that you actually use for classification is typically is the accuracy score, area under the curve, sensitivity. But for regression, you actually look at R square or mean squared errors. That's what you actually try to use. And for your clinical analogy, classification is your diagnosing. Regression, you are measuring. So the measurement by itself does not necessarily give you a verdict. You create the verdict on it. Oh, blood pressure of 160 over 100. Now you're saying, oh, this is hypertension. Now in those GNCs, this is stage two. Or so that's how you actually can understand. Whereas classification, this patient has cancer or no cancer. This patient has a foot or no foot. Like as simple as and black and white as that. Okay. So when we talk about the branch of what we call supervised learning, there are so many different algorithms that we want to talk about some of the few ones and try to also contrast them to better understand how the machine thinks and how it makes its decision. So that again, the type of data it used is actually reliable on you to label it. So this is your labeled data set: apple, orange, orange, apple, orange. You train, and then you put the test data that you have not labeled, or you actually know the label, but you're not telling the machine what it is, and you see how it predicts. It actually predicted the apple and the orange accurately. So this one is 100%, for example. So it makes a prediction, it compares it to the true outcome, and then adjusts itself to better know where it actually stands and try to minimize the error that actually can go do by iteration. So these are the two probably commonly thrown around word when you actually look at machine learning, and actually in any analysis like in healthcare: linear progression and logistic regression. Linear regression and logistic regressions. So just to also make it simple and to, while both have a regression label, linear regression is more for continuous values, whereas the logistic regression is about the logic that is binary. So I'm converting whatever actually I have into like a verdict, yes or no, A or B, or this is type of a kind of a decision it makes. Instead of actually just regressing to a number, it actually makes it a classification type of analysis, although it has regression in its name. So typically in linear, you're looking at something like blood pressure, length of stay, numerical data that is direct, measured. And logistic regression is actually a category: diagnosis, mortality, a 0 or 1 probability, right? And it, again, look at this one looks as a mean squared error, and the other looks at the sensitivity, specificity area under the curve. And like for linear, you try to predict what the cholesterol level will be for that patient given all the parameters that you have given. And the other one was saying, okay, is the patient likely to be dead or alive given that what I know about them at the end of this study, or at that column of dead or alive that I have in this sheet that I need to fill to see how am I scoring. Okay. So other techniques is one called support vertical vector machines, and another one called decision trees. I'm trying to contrast them, not necessarily because they are related or like cousins, but just I want to show you how it actually works. So SVMs basically try to classify. Most of the time, they try to classify into two classes, sometimes more, honestly. You can do it for more. Decision trees is much more like versatile and robust, and can actually put multiple classes together. SVM really it can handle like tens and thousands of features. Because you only have like two classifications or maybe three, you are able to run through so many training lines and make that decision because it's A, B, C or A, B, versus when a decision tree, it has to actually follow the flow that you actually create. Let's, for example, this is a good example for any algorithm that we use in healthcare or flow sheet or whatever decision tree we make. Oh, if this person comes in and they have this, well, if they have this and it's yes for this and no for that, it goes to different pathways and then yes and no, or a numerical kind of bifurcation and a bifurcation under one bifurcation. This is how you can imagine a decision tree, like exactly what you actually think of. So it's very like hard for it to actually do a lot of uh, features together. Uh, and also, it has a lot of complicated decision boundaries, right? Um, but SVM is like there is no like a very simple decision boundaries. So it does not necessarily end up overfitting because it's just like it doesn't have a lot of assumptions before. It does not have a lot of if then, if then, if then. So SVMs is very useful in stuff like text classifications, spam detection, computer vision. Whereas, like if you're talking about decision tree, like profile classification, in terms of like, okay, based on this, I'm gonna predict they have COPD, stage so and so with that type of things. So again, it is a simple decision tree. An animal tree has feathers, true or false. So if it's true, can it fly? True or false? Then, oh, okay, it's a hawk versus penguin. Does not has fins. Okay, well, it's dolphin or a bear. So it can, if it does not fly, then you're asking it, does it actually have fins? Of course, these miss a lot of the other potential classifications, like where is the human, where is the amoeba, where is the lion. But based on these, you can actually end up with four kind of different categorization. That's why it's actually a bit overfitted because you put these in the real-time data, and maybe the human will become a dolphin, or the lion becomes a bear or something, because based on this logic, there is no other option. It has to put it in the under a certain category. Okay, whereas SVM looks at all different kind of uh, data points and try to classify to say, well, these seems to be belonging to this, and these seem to be belonging to that, and these are the hyperplanes that separate, like, and I spread them apart, and this is what I'm going to use for any future point to tell if it's A, B, or C in this example. Okay, and there's something what is called a kernel. A kernel is an area where you actually can use it in more than this is a 2D dimension here, what you see in the left upper corner, and then when you convert it to a 3D in the lower image, you can see that they actually do not live in the same plane. So instead of you actually taking all of them and reducing them to a single plane, or try to calculate where would they fall on that plane, you take whatever they are in that 3D and say, this is the decision surface. Whatever is underneath that, I'm going to consider this, and that I'm going to consider that. So this is a very important kind of aspect to know. So SVM is nonlinear, again, kernel-based, where you actually have a hyperplane that actually decides. Decision tree is nonlinear, it's very rule-based. So the output is typically very kind of like hierarchical and like distinct. So it's like rules and thresholds. Interoperability is very high because you know exactly how it's taking the logic and how actually it reaches it. Whereas SVM is a bit of a black box because I cannot see the hyperplane it created for 15,000 variables, right? I can imagine 2, 3D, maybe or something like that, but I cannot envision 15,000 dimensions and a plane between all of them. So that's actually how it handles stuff. Okay, so is it able to handle nonlinear data? Of course, SVM is perfect for that, and so is the decision tree. But this is very important. Outliers. Okay, anything that is an outlier in SVM, because it now has kind of a physical, geographical kind of a location for that data point compared to the rest of it, it's really able to tell, oh, this is a very far-fetched, probably less likely to be part of this. Whereas for decision tree, it will probably overfit something that has not thought of in one of them. So it's not a very good outlier mitigating technique. So if you want to classify an image or an EKG, SVM is great. If you want to make a clinical decision model for your decision tree is your guy, basically. And again, kernels are different types. So there are linear kernels that there's no mapping, assumes linear separation, so predicted mortality. Polynomial kernel has a higher degree of polynomials, so it's actually help you tell more than two categories necessarily, like classifying tumor type based on biomarkers. Uh, uh, RBF basically is it calculates like a different distance between different points, and it's nonlinear, so it's very good for imaging like MRI, EKGs. A sigmoid kernel is like a neural network. I mean, we're going to talk a bit more about neural network because that's probably the most hyped and the most common models, it and its kind of derivatives uh, going forward. So, linear kernel, really, it's a clear glass. You're not doing any kind of a uh, refraction or manipulation of what the view is. Like real data as is. RBF is like a magnifying glass where you say, okay, I'm going to look at this specific area, give it more weight, and try to see it. Polynomial is like I'm actually in an area where there's not only one magnifying, there's a magnifier and a shrinker, and a magnifier and a shrinker. It's like these mirrors that you go to in a carnival, the curved mirrors. So it is very complex for it to try to kind of highlight some areas and make other areas less important. Okay. Going forward, there are what they call random forest models, and there's the KNN models. So the random forest, the easiest way to think of them is you have like a worlds of parallel universes all running decision tree makings. So you have a decision tree A, decision tree B, and C and D, and so on. So, and each one of them is like a different scenario in a different dimension, a different world. Like, oh, this is a different universe, and I'm running as if this is a world, this is a world, this is a world. And in each end of them, a decision is made. And then what happens is the model votes by majority. Oh, and these 12 universes that are parallelly running, seven said yes, five said no, therefore it is yes. Okay? It takes a lot of training time, but the prediction time becomes really slow. KNN is a different story. We'll talk about it in a second. And because it's kind of a structured hierarchical model, you can understand how it actually operates and actually take that operation to something else. So it's very important to understand that. It's very good for like large data sets. KNN is a different story. Let me try to show you the image. So this is for what is random forest like gonna be like. So this is decision tree number one in the universal number one. It is a result number A. Same for decision tree number two, so and so until n. And then whatever these n has voted, who had the most votes, and this is how you actually create the final results. Whereas k and n is an interesting, so it's a k near a neighbor. So it looks at the data point and say, which one is the closest to me? Or which so and so are the closest to me. And the K is the number of how many neighbors you're going to look at to decide where you belong. So you can say KNN of 3. So I'm going to look at the three closest neighbors and make the decision based on how close do I belong to which one of these groups. Or K of 17. I'm going to take the closest 17 points and decide which one I want to belong to. So it is very interesting that how K, when it changes, it can actually change the outcome. For example, when you say K equals 3 for this yellow box, it actually belongs to class number B because 2 out of 3 were within that circle. But if you take K equals 7, then now actually you've added one class B and three class A points, and it actually flipped into a classification of class A. So it is important for you to understand what the K tries to do and how it influences the outcome and how what's overfitting and underfitting in the model means. So it basically takes a data point and based on the K parameter that you put, you say it belongs to this or that. It actually is very sensitive to how many Ks you do. Okay, so keep that in mind where you actually can underfit or overfit based on how many Ks you actually end up including in that parameter that is actually going to measure itself against. And then, of course, neural networks. I'm going to give it a brief introduction here. We're going to come back to it to talk more in details because this is also something that we covered in our LLM explanation. So basically, this is a multi-layered analysis where it can be supervised and nowadays most commonly unsupervised, where you put uh, this data and push it to the algorithm and wait for the output layer to tell you exactly which ones it actually or which it's the final verdict. And all these hidden layers are parameters, and we're going to talk more about them in a second. Okay, so I covered like nine, maybe not naive Bayes, but most commonly used supervised machine learning techniques. And again, I am not trying to confuse you. I'm just trying to help you understand what's under the hood when they say this model used so and so for its prediction model. And while everything is shifting to a neural network, a lot of the simpler models, the more robust models that we have in healthcare are decision tree or LR, logistic regression or linear regression based, some of them SVM and KNN. You have to understand all these AI applications that actually are using that were trained on such models. And that's important for us to know because now I know, okay, this one is very sensitive to outliers. This one is not. This one is feature intense. This one is not. This one needs a lot of training data or actually very slow. So all these will help you kind of navigate and understand better with what type of car you are driving when you are actually using these tools. Okay. This is a very summative table. I'm putting it here for reference. If people actually want to ever sit down and take a look at it, it has actually advantages, disadvantages, and best cases in healthcare. I'm not going to put much time on it because I want to use our time to explain more stuff and then maybe talk more about like an open discussion at the end. So, when you have supervised, you have the unsupervised, so the other end of the model of the logic. And basically, what this is like, I have tons of data. I don't have time. I'm not gonna label it for you. Go figure it out on your own. So I have 500,000 pictures. I'm not gonna tell you if it's a cat or a car or a dog or whatever. I want you to take them and put things that look like together in the same categories. So it tries to for itself to look for hidden patterns. Oh, okay, I'm gonna look for stuff that has eyes and a pointy ear or pointy ears. And if they look that way, they're either cats or dogs. Now, based on the size of the eye, the size of the nose, I'm gonna decide this is a cat or a dog. Non-pointy ears, okay, they might be bears or humans. If they're up there, they're bears. If they're closer to here, maybe humans. And now if they're here, too big or too small, that's actually how it actually tries to create these patterns and decide based on them which category or how many categories it's actually going to end up creating. Sometimes they might do two, sometimes they might do like it depends on how what other parameters you put in it for you to use. So you have only input features. There's no output. You're not telling them, oh, find the dogs or cats. No, you're just telling them find the similarities between these and classify them accordingly. So it clusters these datas or these pictures to the ones that it thinks belong to the same category. And then based on that, kind of it simplifies the world for you. Okay. So instead of looking at the picture with uh, 1045 or whatever, 48 pixels by 700 and the other way around 768 pixels. So that's a million plus. I'm gonna instead of taking each dot or each pixel as a uh, uh, data point or a variable, I'm gonna actually just look for variables that are like, okay, I'm looking for triangles. I'm looking for pointy stuff. I'm looking for contrast in color. I'm simplifying this very complex load of images, so actually can actually come up with something that I can quickly run and quickly use. So it works uh, exactly as we talked about in dimensions of this world. This data point belongs to which category, or is this or that based the distance that it actually has between the other data points. So they kind of cluster to each other so they can create these classifications. Of course, it's very helpful because you don't need to train it. You don't have to label the data. It actually might show you stuff that you didn't never thought of. Oh, there's a relationship, like a similarity between bears and dogs. Oh, why? Yeah, now I understand why the machine actually has uncovered that. Oh, you know what? It actually was able to classify certain dogs that you never thought would actually have two subclassifications into two different categories based on its imaging alone. So, like now in like radiology, we never thought that there are some radiological differentiation between different types of brain cancers, for example, or mammogram findings on high resolution imaging, but they are able to because they are looking at data in a different way and finding patterns that we never thought that they even exist. However, on the disadvantageous part, you have to take its word for it. You cannot verify. There's no ground truth to say, well, actually, this was cancer and you missed it. And that's why your model sensitivity is now, or accuracy is 85% versus, oh, I mean, I guess I have to trust you. Or find another way of validating your answer after the fact. So there's no ground truth that you actually can be able to tell the certainty of the decision and the accuracy of it really ahead of time. And again, harder to interpret when it actually throws you all these classifications that you never thought are there. And like, okay, is that true or not? I'm not sure what to do about that with this model. And it requires a lot of tuning because, again, these parameters that in the neural network, remember, they are fine-tuned. The model itself is fine-tuned. So, and also, a domain expertise is a very needed thing. Remember the example of the bit sheet with the Mickey Mouses? The machine has no domain expertise. You do. Like, yeah, this is an image of us, something that's completely out of your domain because you've never seen enough cartoons as a kid, like I did. So this is where it comes to say, oh, there's a dimension that you completely missed because it's not part of the training data. But I know because I'm existing outside of your universe, how complex it is. I'm still seeing stuff that you don't see. Where can you actually see it being used? Well, grouping patients and symptoms based on genetic profiling. Okay, based on this genotype, you might actually explain this phenotype or the vice versa. New disease subtypes for clinical data. We actually were able to identify the endotypes for ARDS during COVID using these models to say, oh, this actually belongs to this subclass that we never thought it actually existed. And now these actually respond to this type of treatment versus these respond to the other type of treatment. And it actually helps you reduce dimensionality of genomic and imaging data for analysis. Like these are very complex data points. And when you actually make them simpler for your training purposes, for decision-making purposes, it becomes very helpful for you to actually do things quicker and in a larger scale. Again, the simplest way of thinking it, there's no labels. The model figures out on its own where it says this belongs to this or that based on how the data points actually come closer or diverge apart. So again, it is based on clustering. Unlike supervised learning, which is classification and regression, this is pure clustering of data points based on whatever criteria it actually creates. Of course, there are tons of models. These are the five most common ones, or six here mentioned. We are not going to talk necessarily about them in details, although I put a couple of slides on them with details, but this is not the point of this talk, especially with the unsupervised. Because of its black box nature, it is hard for you to kind of tell one from the other, unlike the data that is, I'm sorry, the models that are supervised, where you can understand the logic. The black box nature of this becomes a challenge for us to say how arbitrary the results are versus how logical or grounded in truth, as we mentioned. So we go back to neural networks, the different types of them, but in general, we're talking about something that simulates what you guys are fond of, which is neurons, and see how they interact with each other And I don't know where you guys stand on the theories of neuroplasticity. Well, there is some form of neuroplasticity that happens with training where these pathways are like more founded and tighter and have a lower threshold versus others. So they're going to fire more based on this or that. And it actually is layers and layers of data, of parameters that actually end up making the final decision at the other end. So weights and biases are something that you actually end up measuring and creating weights for them and scores, and then you can actually then say this pathway is more likely, this pathway is least likely with each of the scenarios that actually go through. So this is like a nice GIF picture or GIF picture, however you want to pronounce it, to show you how the neural network layers work. And you see it starts with 4 points lighting out, like three whitish and two grayish, half lit and one unlit on the sixth layer in the beginning. And then as it propagates, you can say there are some wider or thicker lines that connect some of them to the other. It makes them more likely to be the ones that's going to be carrying forward. And then based on that, what's the next commonly sought route or the thickest line to the next layer, and that's how it actually works. And these thicknesses and thinnesses are what's happening with the training. This is how the model becomes to say this is the most likely sequence of stuff based on these inputs. The same way word finding we have in like whatever Google search model uses is the same thing. Was the most commonly associated next step. Okay, so typically it starts with an input and then an output will actually tell you what the decision is, and that's how it actually works based on analyzing hidden features or by hidden layers to come to this classification. So it there's input data fit into this network that was pre-trained. The network makes prediction and forward propagations based on its weights, and then actually measures between the prediction and the true value that's calculated as a loss function. This is a bigger discussion that we can have now, and then actually that's how it end up saying this is the cluster that it belongs to. This is the cluster that I actually ended up putting together as the outcome. So, and errors typically are sent backwards. So this is how it actually end up knowing because it iterates and based also on our sometimes our feedback afterwards, what we call like, for example, reinforced learning, which is a model we're gonna also talk about. There's a gradient descent that helps the model actually becomes better. So there are many types of neural networks, what they're called feed forward, with the basic type, where data goes one way, like in the image layer input, and then layer one, two, three, four output. It only goes this way. Okay, there's a convolutional one. Okay, so this one is specialized for images. So it's convolutional, again, from the word. And there's what they call the recurrent neural network. So convoluted is very helpful in image classification, radiology, pathology, so and so. It does amazing with that because it's able to quickly kind of learn and fine tune and go back and reweigh its parameters. Recurrent neural networks is for sequential data like EKGs, like speech, like time series. It's able to actually do that because this kind of a sequential nature in the data. It's not like one image. It's like oh, there's a sequence and the time in the EKG or EEG or whatever you look at. And there's the transformers, which of course is the kind of the model that actually have created all these large language models. It is a type of recurrent neural network, a variant with longer sequences, and actually based on that, you've actually created these weights and have fine-tuned them. So where do we see them being used? Of course, medical imaging. Medical imaging has been the front runner of a lot of AI in medicine, whether it's like detecting tumors, fractures, lung pathologies, X-rays, MRIs, EEGs, EKGs, all of these. Diagnostics, trying to get disease protection from EHR data. Of course, that field is the least developed because, again, garbage in, garbage out, and our EHRs are full of garbage. There's completely useless data, as we spoke in the lecture about clinical applications of AI. Genomics, amazing field, amazing applications. we still do not understand fully a lot of aspects, although we have had the Human Genome Project completed and we have all these kind of knowledges. There are so many layers of complexity in genomics, epigenomics, like factors that are both intrauterine, environmental, so on. So it is so hard. Of course, monitoring, analyzing EEGs, EKGs, patterns. This is an area that really actually has a lot of acceleration too, where you have this high resolution data and you can come up with stuff from looking at that data. Drug discovery is another way of you being able to use like neural networks, and of course, clinical NLP, converting our noises that we produce with our tongues and lips and vocal cords into words that actually they get gonna figure out and say, okay, he meant this word, not that word. He meant this context, not that context. He said do or didn't, did or didn't, could or couldn't. All these are stuff that they try to imply from the conversation, from other parameters that they can actually pick on, the speed of announcing it, the tone of the voice, so and so, because again, these are most of the commonly kind of flipped or mistaken things. So it has to rely on other data points. So neural networks is amazing tools to actually look at stuff that we don't necessarily think of as differentiators, but are for the dimensions of the machine learning eyes. Advantages: can deal with very complex nonlinear data with nonlinear relationships. Amazing. Very, very able to kind of look at high dimensional data, images, text, signals. And actually, the more data you put, the better it becomes. There's significant improvement. Of course, it plateaus at one point, as we see with what's happening with LLMs, but it's still, when it gets novel data that actually helps it create new dimensions, new weights, it actually will do that. Of course, it needs large data sets and a lot of computing power. That's why two-thirds of the electricity being produced in the US is going to go to data centers nowadays for powering AI models and LLM models. They are hard to interpret, black box. We don't know these hidden layers. And even now that we have models that actually can try to explain or like declare some of these layer like decisions, it's still hard to know why did we say this way is heavier than the other, and this is the pathway that this parameter is going to take every time it's being faced, or 80% of the time. So it is very hard for us to actually understand step by step, unlike something like a decision tree, right? And of course, there is always what they call overfitting, because you have so much data, you overfit to whatever you encounter afterwards. And remember, when we talked about LLMs, the way transformer works is we convert the input, which is now language, again, large language models, into tokens. So we, instead of taking the image and looking at it as pixels or at contrasts of colors or structures, we look at words as bits of information. So each word becomes one, two, sometimes three tokens, and then it's divided, and then these are fit in this input layer, and then it actually starts to propagate forward. So roughly, if you have 1,000 tokens, that's 700 to 750 words. And of course, in the more the tokens you have, the more complexity and need for processing need. And of course, tokens are not equal. So the more text you put, if it's not equally important, actually they get at the first layer the same amount of interest, or the predetermined amount of interest before they go into a certain level. So remember this image, if you remember, data visualization empowers users too, and then it goes all through all these hidden layers for it to decide, okay, what is the next best word? And when it gave the ways, eventually was saying, okay, visualize is the most common, but it's already part or of a root of the word that is used there. So it makes no sense to repeat it again. So I'm going to come with the next best thing, which is create. So that's how word prediction models work. It just like tells you, well, data, when it goes to this query, the most commonly associated word with, when in this group, it goes to that layer, and then gives you ways and weights and actually vary, and then eventually you get one one after two to what? To visualize, create, see, make, so and so. And remember, we talked about temperature and Ks. We'll also talk about them in a second. So the parameters are exactly these weights that are happening between different data points and how thick the connection will be, how most frequently going to be suggested or used as the way of determining the next step. Uh, and they are proliferating. And basically, in each model that we actually have seen coming through, the parameters have exponentially grown, maybe plateauing now. So ChatGPT 2 had 1.5 billion parameters with a B. ChatGPT 3 had 150 times almost that much, or like 112 times, so 175 billion. And then ChatGPT 4 went to 1.76 trillion, so 10x, but this is unofficially confirmed. And then ChatGPT 5 went another 10x to 17 trillion parameters, according to CFO in one of the conversations that they had. So you can tell this is a huge amount of kind of training that happened for you to create all these parameters. More parameters, better understanding, better complexity handling, but also higher computational cost, higher energy cost, slower, right? All these are important stuff. That's why this technology do not scale well. So there's a max X K or a top K sampling where it says, okay, I am going to determine how many of the potential outputs that are there I'm going to take into consideration to take to the next level because I cannot take all the potential associations and propagate it forward. I'm going to only take five and actually guess what these five is going to be. And then based on these fives, well, I'm going to take the next level. So if you have a K of five, then the model chooses the top five words. K50 actually uses the top 50 words. K1 is like the most commonly used word, only that word is gonna only be the one I'm gonna be used. So the lower the K, the safer it is, but the more repetitive the output, the higher the K, the more variation and surprises and hallucinations that you can get from that. And of course, imagination too, and creation. So when you say I'm gonna take the top K being number three, I'm gonna take the three commonly the highest affiliated words. So mat, table, chair. This is how she's gonna decide which ones actually I'm gonna take from the series of next words potential. And again, temperature is something we spoke about. Is briefly to comment on. Temperature is like how much randomness I'm going to actually tolerate as I'm actually moving forward. If you put it zero, it's going to be the safest response. I'm not going to even try to give you anything outside of the orthodox answer. 0.7, so it's kind of balanced. 1 plus is now actually creative and might be risky. So an example, once upon a time there was, the temperature is zero. Once upon a time, story, all time, princess and castle. Okay, safe. Well, temperature of one. Well, once upon a time we're telling a story. Humans can be part of the story. Animals can be part of the story. Well, robots can be the type of story. What stories do we typically talk about? Oh, mysteries. So robots are solving mysteries. Okay. Temperatures higher. Okay. Once upon a time, there was a cloud of dreams that sang melodies. And now it's actually taking words from a bigger pool. So it's coming kind of a poetic, maybe if you like to kind of imagine this as poetry, maybe something else, maybe hallucinations. And that's why, because what happens now that the cloud of dreams became the next predicted series of the words, they also came the next set of tokens that's been added to the query that's going to propagate in the parameters moving forward. And that's how actually you end up going to hallucination. You add these kind of newer tokens that takes you to a different territory than when you're trying to begin with. You started talking about your homework for math, and now you're talking about die for death and suicide and love stories. So it's like it propagates because these kind of pools of tokens got newer tokens that are associated with other types of conversations, and it slowly reiterated its way away from math into something else. Okay. The third type of models, in general, we talked about supervised and supervised. And the semi-supervised is a kind of a mix of both, where the model is trained on some small amount of labeled data and large amount of unlabeled data. So you actually with both of data. So I gave you some labeled, some unlabeled, and I told you, okay, you know what? Out of these 500,000 pictures, these three are for a cat, these 10 for a dog, these are 17 for a car, these are for humans, but these 4,000, 100,000 left, I have no idea. You go figure it out. So you give some hinting for it to actually understand how many uh, clusters, how many kind of outputs you expect to it, and then it goes in self-trains, or it goes in code trains where you actually have a model that actually labels data for each other, or they actually use a graph-based model, so they put all these clusters as graphs, and they actually also create kind of a dimensional and geographical relationship between each other. So how is it helpful? Again, we talk about images. That's exactly what it thrives on or works best with. So image labeling. And of course, similar to imaging, we have plenty of, and we have no idea how to deal with websites. Also, tons of data in that, some crap, some meaningful. You have to find a pattern, and then this website is actually a porn website, despite not having any word of it. But now actually it is. So actually, my paternal filter would block it based on that similarity. This is a commercial website that your work is not allowing you to go see. Based on that, it's actually how it determines you're not allowed to go to this website. These are all examples of tools that you actually see in your daily life to figure out how this actually is being implemented in real life. Of course, reinforcement learning is the what I want to say, the Maybach of models, because these are models that are designed to actually be able to uh, learn from its mistakes to optimize for the outcomes that it's actually looking for, not only momentarily, but over time. This is the most important part. It actually maximizes the cumulative reward. And when you're cumulative, you actually have to accumulate, so actually need time. So whether it's personalized treatment planning, decision support making, drug discovery, medical imaging, radiography, robotic, all these are stuff that you can go back or create a pipeline in the model to say, well, you know what? This robotic surgery approach did one, two, and three, and that is why this one was good, this one is not good. And then based on what you kind of reinforced, it's gonna see whether it did right in the first time or unique in the first time, and propagate that, or do it again, and what it did wrong to try to avoid it. So uh, basically, if you're thinking about a medical analogy for reinforcement learning, an AI system for this support model is what comes to mind. It interacts with a very different environment from what you might think. It might be a hospital system, it might be physiological state or physical state, or a psychological state sometimes. Okay, the state that they look at current data, labs, vitals, condition at the time X and or T, and try to figure out what could be happening in the future, and kind of keep iterating based on when that future point reaches, what was the actual outcome versus the projected outcome, and then okay, I'm gonna reiterate based on that. So it needs live data sets that are uh, expanding with over time. Okay. And then the action that you're trying to do, give or not give medication, order not order test, change or not change vent settings. Okay. And you put the reward. Okay. The less people you kill, the better you are. Okay. I hope we agree on that. The less complications you do, the better you are. The more stable the vitals you obtain, or the glucose that you actually control, the better you are. So you, as an insulin pump, that you're smart, this is how I'm going to judge your outcome, or you're going to judge your outcome, because this is how you enforce. Oh, if you hit above 180, you're bad. Slap on the hand. Oh, I'll learn next time. They've used this to actually train the most successful, most important models, but they actually tried with game theory or with actual games. That's how they actually did. Say, aim for the highest score, or aim to actually play against yourself and see how you can actually win, or do all these kind of simulations of potential plays in Go or chess to actually see the best strategy. And every time you actually win with the least amount of steps, that's how you're gonna say I actually did better. So it is actually very important to actually create these kind of treatment protocols that are AI learned because of all this data modeling you have done as well. So, uh, protecting, so state, you're looking at blood pressure, heart rate, lactic urine output, and you say, okay, I'm gonna use adjustment of pressures and fluids or antibiotics to say how I'm gonna improve outcome by improving survival or decreasing the amount of organ failure. So over time, the combinations of all these adjustments will become something that you can actually feed back to the machine, and then it gets better and actually ends up having something that will help you manage sepsis in the ICU. And Mimic 3 is the largest that I know of. De-identified clean data set for ICU. It's out of MIT and Beth Israel Deaconess Medical Center and Boston. And this is what they used actually that model on, and had a paper published in Nature in 2018 talking about how they actually create a reinforcement agent that was helpful in optimizing sepsis management for ICU folks. Um, that data set, however, is static. So what they did is actually try to mimic that actually there was a propagation of time for it to predict in the future, because they don't know what I mean, they've known the end story for that patient, discharged, deceased, so and so. But for the training model, they were giving it on chunks of data inputs, and that's how they actually were able to do the study on that data set. So basically, can give you treatment policies close to what an expert would have done. Sometimes maybe actually maybe superseding it. We'll see how these will kind of prove themselves in real life data. Again, Mimic is clean. Mimic is not the actual data set that you have that's full of stuff that makes no sense. And its documentation and its lab errors and everything else that's there. So again, this is a reiterating process. There's a clinician, AI agent, maybe taking action, and there's the patient, it's the environment, and then there are improved vitals, which are the words, and there's a state, it's actually being monitored. So there's an environment and there's a state, and you actually try to iterate these to actually until you get an improved reward. So it learns from experience, right? Because it actually can experience thousands of ICU episodes together. It adapts to variability of patients. Oh, when you encounter people with heart failure or diabetes, this is how it's actually different. This is how I'm going to weigh having that uh, in the model going forward. It focuses on long-term outcomes, right? It actually looks at the end game, win, lose, death, alive, failure, no failure, right? Or achieve, not achieve the goal. So it's actually focused not on predicting what the model tells you now, right? It predicts on what the end game is. There's a goal, there's a score that actually it plays to achieve. Challenges. It is hard to define what a reward function in medicine. Is it survival? Is it comfort? Is it quality of life? Is it hospital length of stay? Why do I need to ship them out of the hospital quicker? Right? So all these stuff, it's hard for us to kind of also translate into a meaningful stuff for humans that are also machine uh, detectable slash predictable. Data quality and availability. Uh, Healthcare is again spotty in its data. Its quality is really bad. So that always challenge you how I'm gonna able to reinforce a model when I only have an encounter that is sporadic. It's not having continuous data. A lot of data loss. A lot of data that is incomplete or non-continuous. So this admission, you did MRI, you did EKG, you did troponin, you did fluids. The next admission, you're actually doing something completely different. You're doing an X-ray of the knee, and in lab work, it's different. Safety and ethical constraints. These are black box models. How can I actually assume that they're safe? And is that ethical for me to actually give these decisions to machines? Observability. Okay, I cannot see the entire process. I'm worried about that. What's being used to kind of titrate, how it's been titrate. It's a very dynamic environment, right? Because now, like a second ago, it was doing that, and based on the reinforcement, it's now doing something different. So how can I actually be able to uh, judge on the environment or a state? How interoperable that is? This mimic data. the paper, can I go and put it in a model that is actually part of Epic and then they predict sepsis or treat sepsis for us? Maybe, maybe not. Again, who's legally kind of accountable for this? And again, this is complex, computationally very complex, data design complex. The reinforcement mechanism input is very complex. How can I feed the data to the patient from a patient after they're discharged? What type of data I need, so and so. So it's not an easy model. It's a very nice model to have in real life when you actually can actually have people sit in a lab being 100% observed all the time, the same measurements. But that's not how real life scenarios work. Okay. And of course, that's why bridging offline learning and real world deployment is a big challenge for these models because these are not stuff that are live and approachable and accessible and measurable all the time. They are not. We are humans who are actually going to disappear and want to disappear and that do not want this and that being implemented on us afterwards for reinforcement purposes. And of course, are you going to accept that as a clinician, as a patient? How are you going to integrate it to your workflow? All these are questions that you can actually always raise and think of. We're approaching the end of the time. So again, how can you actually remediate that? Try to no, kind of talked about these problems. These are the challenges. Now, solutions wise, how can I better define the reward function? Maybe actually I need to combine metrics like stable vitals, quality of life metrics, and so on. So, sparsity of data. Again, you then try to do like steps to help abstract that data. Sometimes you actually have to do what they call imputation. Imputation basically you guess what it would have been like. So ingenious, also dangerous. Yes, I didn't have your blood pressure measured in that hospital stay or like that clinic visit stay, but if I was to guess, I would guess it would be that much, and then I'm gonna put that value on it on your behalf. It's like, yeah, but this is how like, because again, no patient is a trend. Maybe population will be a trend, but the patients are very hard for you to actually convert into just kind of a trend. So all these are challenges with some solutions, but are also not necessarily going to be the silver lining type of solutions for a very complex problem in a very complex world of healthcare and human. Limitations, again, data quality is an issue for us. Inability to understand context for a machine. Metacognition, learning about learning is some machine is lacking, and they can be tricked the Tesla camera scenarios, the whatever. I mean, we have so many scenarios. Cost is it worth all this money? Remember, we need to talk about that Stanford EKG model that predicted with high certainty, but it cost $27 million and didn't change clinical practice. Well, was it a good return on investment? No. Inaccurate data analysis, biases, black box nature, no ethics or emotions. Uh, uh, cybersecurity concerns because they're actually going to be targets of attacks, lack of common reasoning, and lack of experienced data science from our field to go tell those folks in all these AI companies like shut up and stop doing what you're doing because it's stupid and it's harmful. All these are stuff that are going to be limitations for real-time impactful models. And uh, why not use models? Because pre-running models will become their own reality. And based on that reality, they're going to have a very different universe than ours, and it's going to become more and more mediocre and more wrong, and eventually going to be meaningless. Okay, remember, data is the fuel of machine learning and AI and everything. Data is temporal. Every time it actually has a different value and it's contextual and does not tell you anything. It just doesn't have a message. The message becomes from yours. The insight is yours. And no, it's predetermined, that meaning this is fixed. And when it simulates, okay, yes, the heart rate is up because they're under stress, physical, emotional, otherwise. That's why it goes up. So when it actually assimilates, it's different from its predetermined. And then think about the worst thing that happens when you actually use this and what kind of error it can result in. And then thank you, and we'll open for any questions.
Thanks, Dr. Abdullah, for the amazing lecture. You basically put all this source code together and simplify it for us. And while people can put their comment or questions in the chat box, I have one comment and one question for you. The things that you mentioned about the bias in the foundation large language models. One of the examples was Grok, for example. In the last news I
Okay,
heard,
Hitler.
if
Okay.
you ask it, it's biased to the founding person. It can give you different answers. If you ask about somebody the person likes or somebody the person doesn't
Yeah.
like, that those are important. I think my question for you, does it matter if we know the black box or not? If we follow the hybrid approach, it seems like hybrid is answer for everything nowadays. If we keep the human in the loop and supervised humans and the domain knowledge, doesn't matter to know where this information is coming from, meaning that yes, we are contributing in the data for ChatGPT and all foundation models, but that is not necessarily bad if we know that we can test what's coming out, the output. If I have the domain knowledge to know what's coming is garbage or not, it's okay for me to contribute at not knowing how they are processing this. And we leave it for the experts like you. For example, all the apps and the softwares that we have right now, I don't know the source code of them. I don't know how they created. I don't know Python, but I
Hmm.
can know that this calculator is giving me wrong answer or right, so I will take it or not take it. So I wonder what's your thought or insight on how to move forward in dealing with these foundation models that are becoming better and better and solving our day-to-day problems and making us way more efficient right now.
So yeah, when it's black and white and we can tell actually with certainty that's wrong or right, like how many times are you able to verify what ChatGPT is telling you? A lot of time you're asking because you don't know, right? And this is an important part of like how much trust we give to the answer and how much we can delegate to it. And this becomes a problem with sometimes you might be able to see it immediately, like the error or the mistake, like, okay, you're driving and it's telling you you're out of the lane, but you actually are going from one street that's 3 lanes into a 4 lane. So it's going to be, you have to kind of drift like that. But you understand the context and you understand why it's making the mistake. So just knowing how it makes the mistakes can tell you how to mitigate it for a better model. It tells you when you actually expect the next problem that's going to arise from it. So, and these are stuff that we don't leave at home. It's not something that always end up like you're at the end of the pipeline and you're having a faucet and you open it. It's predicting your next video. What's your son's watching? How you gonna? What's your patient's gonna be reading? What type of? All these are stuff that really are important that are actually not only influencing us at work or at a single task. It is everywhere, and us understanding some foundational knowledge about that and knowing how these models work will say, this is why I'm ignoring you. This is how I can make you better. And this is how I can tell this entire sector of, oh, AI in healthcare trying to automate a physician. You guys are clueless and stupid, and good luck for you wasting all that money. But I'm not gonna be scared. So just understanding where you're standing in this world of like a lot of uncertainty. Oh, is AI gonna take our job or not? Right? You understanding what your job is and what AI's logic is, now able to say, well, you know what? This prediction of 60% of human jobs being gone in a lifetime, I can tell you we're good for 10 years. 10 years is enough for me to plan a lot of stuff. It's not like, oh, 2027, we're going to lose the jobs and there's going to be a revolution. I don't know if you've heard about Project 2027. These are stuff that are being thrown out there. So it's a philosophical discussion. It's a scientific one, and it is stuff that we need to kind of at least get the sense of where we stand, not necessarily to understand the technique and replicate it, but to see how we can navigate our way around what these techniques are throwing at us, whether it's in the car, and our social media, and the self-driving or driving assistance, or in your CDS and the AHR. So this is why actually I think these are valuable. And I hope I actually inspire one, two, three people to say, oh, you know what? A master's in data science, 30 hours, let me do it. And I want to become someone who drives that because I attended this lecture by this young lady here who works for an AI healthcare company, and she was boasting about all these stuff and like how they're better than us and so and so. Like she is completely clueless. Honestly, I mean, some doctors who didn't know anything about AI or like had marginal knowledge, they were wild and they scared. But for me, it was like, this is a freaking joke. You think you can actually automate this and that? Like we don't even have the data to know how we're making the decisions. Like remember from one of my talks, we talked about 80% of all pediatric cardiologist decisions have no ground in any literature you can actually say right or wrong. Your job probably has even less data on what you do to say, okay, is it right or wrong? What the guidelines say, because it is so hard for you to actually put a decision tree on how you think and how you apply it in your work. Impossible.
Yeah,
The what ifs are so many.
I think we are saying the same thing. Is like
Yeah.
it is important to be versed in the foundation to understand how this thing works, but we don't need all of us to become expert in it and become a data scientist. And if I ask the question a different way, is the
Hmm.
efficiency rather than the knowledge. For example, before, if I want to run a study, it would take me from writing the proposal to submit to the ethics, and then to find a statistician who will run the analysis, somebody to collecting the data, and somebody screening the data, writing the paper, sending it to somebody to proofread it, submit it to journals, and so all this it will take about maybe you are looking at a year or so to have the
Hmm.
study from idea into publication. And now with AI, you have a legions under your fingertips. If you know the domain knowledge, you can use them to make yourself much more efficient. An example being like the Julius AI, one of the models, they use R itself to run the analysis on the data sheet that you have given them. So that was my point I was making is it does make us more efficient if we are not at one of those extreme. One extreme being that lady that you have mentioned that they are worshiping AI, and then another extreme they are completely vilifying it and saying no, AI is wrong, we shouldn't even touch it. So somewhere in between, if we embrace it and use it to our benefit, I think it is game changing. I see it in my kids. They cannot take the way of teaching anymore. Like well, my son was telling me his teacher was explaining how to make formulas in Excel for hours, and then with the foundation models, he just asked the question and it create the formula and integrate it into Excel sheet. I think the way I think of it, it's some of this is becoming just like exercise. You make it to make your body look better, not to really run or walk to your job anymore. So that shift, I think we are still figuring it out, but there is so much coming out and so much benefit of this.
Yeah, as you probably told your son, you said that a couple of sessions ago that this is going to be the new calculator. We have to learn how
Yeah,
to use it. I don't know. He told you or you told him.
he
That
told
is
me.
absolutely true, and there is this kind of if like, why domain expertise matters. Like I was running some analytics on my Nasher app, like the audiobook platform, and like, oh, this book actually had this many listings. Like, no, impossible because I just uploaded that book like 3 weeks ago.
Mhm,
Impossible for it to do that.
mhm,
This is how, I mean, this insight of you, and then you can say, okay, why did this calculator get it wrong? What type of formula errors? And this is what actually that understanding, okay, and your son is missing out on not learning how these formulas work because that's the most important part. Because yes, I'm going to automate that, but the same way I'm teaching my daughter to add and subtract, she can do it on the calculator. But the mental exercise for it now, it says, okay, and I tell her, 86 minus 15, you have to understand that there's like a rule that's not going to break. The outcome is never going to be more than 86. Impossible. And for her, it took a second and said, oh, why? Then for a second grader, then now she understood. Now she knows whenever she encounters a problem like that, whenever the answer is higher than that, she knows, oh, impossible for it to be higher than the original value. So this is the type of thing that we need to come up. infused by these talks. Like, okay, I'm gonna give you microdoses of logic of the machine, so you can build your own logic about what the logic of the machine is, and then to interpret what it comes out from. But yes, I agree with you. Like, I do not run analysis nowadays on Python. I'm doing ChatGPT. Here's the
Yeah,
data set. Look at this variable, use this tool,
yeah,
and I verify it. Like, okay, I might do it on a second iteration, like a second model or a second session, and make sure it gets the same result. But I'm gonna do that. I'm gonna go again and write a code for an entire formula on Python again. So
yeah. I think
that's here to stay.
the key word you said that it's a mental exercise, and it is very, very important. I had very similar experience to you where I created a movement assessment application using ChatGPT, and this halo effect of how beautiful the model is, it can deceive lots of people if you don't know
Yeah,
that domain knowledge. So I ran it on two babies. They were completely different. They gave me very close scores. I said, this cannot be. There's something wrong here. These are
yeah,
two different baby. And exactly what you did, you go back and you say, what went wrong in this model? And that's the only way you refine it and make it work. That back and forth hybrid model between the master, which is still the human, and the slave, which should be still the language model. Yeah.
yeah.
I don't see any questions, Abdullah. Thank you so much. We kept you for 16 minutes after the hour. I will
Absolutely, it was a
convert this and
pleasure.
add it to our channel. This has been a great session. Thank you so much.
Thank you.
Have a nice weekend.
Bye,
Bye bye.
everyone.